This is an example of non-directional hypothesis testing. In other words, two-tailed hypothesis testing. So let's look at this example. Okay, in this example, scores on a cognitive functioning test have a population mean of mu 880 and a standard deviation of sigma 20 and are normally distributed. Researcher believes that antioxidants have some effect on cognitive functioning in the population. Some effect, it could be either positive or negative. And he plans to give antioxidants to a sample of 25 people and measure their cognitive functioning after they've taken the antioxidants. This is a really typical, research setting. However, he is not entirely certain if the effect is positive or negative. Thus, he would do a non-directional hypothesis test. Okay, so when directions are not certain, you usually do a non-directional hypothesis test, and this is a difference between directional and non-directional in terms of setting alpha level. In other words, for when the directions are not certain, you set the alpha level really small, to be sure, it's the actually, if it's, the result happens to be negative or positive, if it's so really close to the center, it can be just due to error, it could be just a fluke. So, but if it's really far away from the center, in other words, if the alpha level is so small, if the z-score for alpha value is way, away from the center, either direction, then it's when the value falls into alpha level, it's really almost reliable that this value was positive or negative. So that's why. Okay, let's move on. So this is a setting. It's really similar to the last one. So population mean was 80 and the population standard deviation was 20, and we sampled 25 out of the population, so sample size 25, and we calculated the mean of the sample of 25, and so we make a hypothesis. Our null hypothesis is that there's no effect in the population. In this case, we're not saying no positive or no negative or anything like that, so it could be either. So a notation is mu antioxidants equals to 80 because hypothesis is that there's no positive or negative effects, so it'll stay the same, so it's 80. See the difference between from the directional one-tailed hypothesis testing, and our alternative hypothesis is that there's an effect in the population. So again, we don't know. You're not sure if it's a positive or negative effect, so you can only say the mu antioxidants after the intervention, it's not gonna be 80. It's gonna be different from anything other than 80. It's gonna be different from 80, either positive or negative. That's why you just say not 80. And setting alpha level is gonna be a little bit tricky, as I said, because we don't know if it's gonna be a positive or negative. So we're gonna have to have alpha critical area in both negative and positive end. So that's why it's called two-tailed, because it's gonna be in both ends. We're gonna still use alpha level of 0.05. 0.05 alpha level of 0.05 in this case, means combined area alpha and critical region is gonna be 0.05. So forget about the directional. It's nothing. It doesn't really have anything to do with it. So it's just gonna use 0.05, for alpha level. That's the main purpose. And okay, so by setting 0.025, in other words 2.5% on this end, 2.5% on this end, setting the critical regions on both ends like this, combined critical region will be 5%. In other words, 0.05, 0.025, and Z score for the alpha value is going to be 1.96, and exactly 1.96, and negative now minus 1.96. Okay, and these are going to be critical regions, and the rest is pretty much the same. Let's look at this research scenario again. The researcher takes his sample 25 people and finds that the mean cognitive functioning score after taking antioxidants is 92. Okay, so the mean of the cognitive score was 92 from the sample, and the sample size is 25. In other words, it's like this. We kind of assumed, this sample was coming from here, this population. That's why we can say this, mean is just sampling, sampling distribution is normal because the population distribution is normal, and the expected value of 80, because of that, and because we assumed this sample was coming from this population. And that's why I had to, Anyway, so let's keep going. What's really important is actually here, the Z-score for this sample mean. Okay, it's 3. 92 minus 80, or 12 over 3. So, in other words, when you look at the Z table, Z distribution, it's here, okay? And remember, alpha level for the two-tailed test is 1.96, so it's about here, and it's not within this, range, which means, you can't really say this value happens when there's no change. You can't really say this value can be found from this population. From this population, you can find values between here and here. That's really highly likely. But beyond this or below this, it's highly unlikely. It won't come out of that this population. But it did, But the data we gather was actually outside that range. So we're gonna have to say this was not true. It came from a population that's not the same as this. That's different from this population. That's what we have to conclude. Z equals 3. Okay. So let's look at the negative 3 right here. So the region is going to be a critical region is going to be the 0.013. In other words, let's look at this. Okay, here. I mean, the critical region. P-value for the for getting 92 points on the cognitive score is going to be 0.0013. That's the probability here. So small. Anything beyond this point, it's going to be critical difference, critical effect. So in this case, it's critical, and it's so far it's same as one-tailed hypothesis testing, but what's different here is you're gonna have to know we got the z-score of 3. In our case, the p-value is the probability I find a sample mean more than 3 standard errors away from the expected value, but we don't know which directions. So either directions could be, that's what I don't understand. Based on the sample was positive in a positive direction, but we can have to assume that it could have been either way, could have been this way. So 3, this time it was 3 standard deviations away this way, but another time it could be 3 standard deviations this way away in this direction. So we say a z-score outside of plus minus 3. So that's why you have to have so you interpret it as like there are 2 possibilities. You could fall into here, or you can fall into this region. I don't really get it, but is that really true? I raised this question, but you're gonna have to assume so, and because you never know. And in that case, it could be this, it could be this, and p-value is gonna be, could be this, and it could be this. Critical region. So it's 0.13% chance that it could be here, and 0.13% chance that it could be here. So total is 0.26% chance that it could be 0.26% that it could have occurred due to an error. That's so unlikely. So that's why we gotta have to assume that there was some positive effect. So my p-value is 0.0026, in other words 0.26%, and my alpha level is 0.05. My p-value is less than my alpha level. Because my p-value is lower than the alpha level, I reject the null hypothesis that there was no change. Observing a sample mean more than 3 standard errors away from the expected value is so unlikely if the null hypothesis is true that I decide to reject the null hypothesis. So conclusion is, we reject the idea that any accidents have no effect in the population. We can say we have found a statistically significant effect. So for non-directional test, I could have come to the same conclusion by observing the z statistic 3.00, which falls into the critical region of the standard normal distribution. This would automatically tell me that my p-value is less than 0.05.